Modulus counters are just typical counters that can count a very specific number and then rotate back. For example, a modulus 6 up counter can count from 0 all the way to 5 and then resets back to 0. That's why you call it a modulus 6 counter, because it has 6 counts in total. I will only focus on building up modulus counters. However, the same type of techniques and concepts can apply to down modulus counters. So an up modulus counters can go from 0 all the way to 5, for example, for a 6 modulus counter, or maybe 7 for an H modulus counter. A down modulus counter can go from, for example, 8 to 0 and then resets back to 8 or something like that. Okay. So let's go to Vivado and figure out how we can actually build such counters. So I'll show you a few iterations of this modulus counters. So we're going to start with what we call a modulus counter hard-coded, and the word hard-coded will be apparent very shortly. So I'm going to follow the three different parts. So it's a synchronous system. So we have the register here. That register has a reset, has an enable, like any of the other counters we've seen, and the output logic is just a number stored. And the inputs and outputs are clock, reset, and enable, and of course the Q. And of course I made it just generic, so the number of bits can be specified in here. So really what's different from a normal counter is just what we could do in the next state logic. So in the next state logic, the way we actually create modulus counters is the following. Well, I need this counter to actually count to a very specific number. I need to figure out what that number is. And the way I'm going to do it in such a way that we can actually make it easier to transition between the different versions of the modulus counters I'm about to show you. And actually, we're going to be using that particular technique in the timers too. So the first thing I'm going to do is I'm going to create a new signal and I'm going to call it done. And that signal, it's actually just a 1-bit signal that tells me, hey, I'm done counting. I reached the final number in the counting. Okay, so I'm going to say assign, and I'm going to say equals done, and then here. When will I be done? Well, when the current value of the register equal that final value. So if I want a modulus 8 counter, that means it counts all the way to 7. So I'm going to do, well, whenever that value is 7, I am done. So the final value is included. My code in this counter and the rest of the counters usually is inclusive. So I usually can't include the final number in here. I just find it easier that way. Okay, so now what do we need to do next? Well, I know whenever I am done, I have like this little signal that tells me you're done. All I have to do is reset. So frankly speaking, all I have to do with the with here is actually to figure out what the next value is. And in the next value of the Q register is based on the value of done. So Q next is just basically, I'm going to say is done. Am I done? If I am, I have to basically reset the next value to 0, because after the 7, a 0 should come. Other than that, I should actually just say qreg plus 1. And that's how we build an up modulus counter, and that's hard-coded because that 7 is hard-coded. And I have written a test bench for you so that we can figure out how it actually operates and show you how it operates, and that test bench in here. So as you can see in this test bench, all I'm doing is I'm actually using a 4-bit counter. So that means it should count maximum to 15. However, it will not reach it because what we did is we made sure that it actually, the final number it reaches is just 7. We hard-coded this, and this is why we called it hard-coded. Okay, and then let's take a look in here. All I'm doing is I'm generating a clock. I'm just resetting and then enabling. So for the first 2 nanoseconds, I'm resetting so that I start with 0, and then I'm enabling it after 2 nanoseconds. And then the first positive edge of the clock, it starts counting, and it counts 0, 1, 2, 3. It does not reach 15, even though it's a 4-bit. It reaches 7, and then resets. Okay, and it resets to 0, 1, 2, 3, 0, 1, 2, 3, and so forth. Okay, even though like we have decided that it's actually of 4 bits. Of course, you might think about it as wasteful. Well, I only need 3 bits, but that's again, you can with like based on the final number. So this counter here is hard-coded. I decided to have it 4-bit, and I decided that it counts 7. I can make it 8 if I wanted to, basically 8. All I have to do is just change this to 8, and it's hard-coded. I just run the simulation, for example, one more time, and that counter now is a little bit different because it should go all the way from 0 all the way to the final number 8, and then go, which I basically just created a modulus 9 counter. So let's take a look at the output in here. So this output in here should show me 0 all the way to 8. This is a 9 modulus. Okay, 0 all the way to 8. Okay. All right. So generally speaking, I mean, there's a lot of designs that will ask me not only for like not to hard code it. I mean, it's kind of like it's not very useful to hard code a modulus counters unless it's a very specific one, maybe a BCD counter that we use it for different things. Okay, that it should be a modulus 10, so the final value should be 9. We'll see that in a separate video. But for now, what I want to tell you is that this particular final value can be actually fed back or fed to my counter in a couple of other ways. In addition to hard coding it, we can actually, or instead of hard coding it, we can just put it as an input to the whole counter. So maybe a system needs to use it in different things. You need to use that counter as a modulus 9, and then you want to use it for modulus 12. You just have to use it differently depending on the situation. So what we can do is we can just add that final value as an input. Okay, and then just code it. So how do we do this? Well, actually, I'm just going to base my code. Most of the code will look very, very similar. So I'm going to base my code on the hard-coded version, and I'm going to show you how straightforward and easy it is to do that. So now this is the hard-coded one, and now instead of the 8, all I have to do is just say copy this, and then now what I have is I have now the final value is not set, it's not hard-coded, it can actually change, and it's an input to the counter. So I can input it to the counter and I make it. So I can change that counter to be a modulo 9 or modulo 12 depending on that input that I have in here. And now here's the test bench for that modulo counter that takes the final value as an input. You can read the test bench here on your own, and you can see that I'm just changing the final value. But we can just take a look at the diagram itself. So the diagram here tells me like I'm issuing a reset and then an enable. And at this particular enable, I'm making the final value 5. So that counter should count to 5 and then reset. So it's 0, 1, 2 all the way to 5 and then 0, 1, 2. And then at some point I'm changing the final value in here. And even though it still counts, but I just changed the final value. So now it will pass the 5, 6 to a 7. And then the 7, after the 7, it becomes a 0. And then goes all the way through. And then here I'm changing the final value to 11. And you can see it just continues as is. There's nothing changed. Okay, it just changed the to 11, and now it becomes a modulus 12 counter because it goes from 0 all the way to 11. So that's how we can do it with an input. Is there another way? Yes, there is another way, and sometimes you just need that counter for a very specific purpose, but you need multiple of them across the system. So you don't want to change them on the fly dynamically. You just want them. And you don't want to hard code them. You just want them to instantiate a couple or 3 of them. So what you can do is we can pass it as a parameter. So a modulus counter that is parameterized. So now the final value, instead of being an input, it's actually a parameter. So when you instantiate it. When you instantiate that particular counter, you decide whatever it is, and you never can change it. Kind of like the hard-coded, it's just parameterized this time. Okay, so how do we go about this? Here's how we do that. So I'm going to go to the input version. I'm just going to base my code on that. Okay, we're going to just do that here, copy, and then I'm just going to paste in here. The majority of the code is very, very similar. Now there's a few differences in here. Because I pass this as a parameter, I can easily figure out what the size of Q is with a different parameter. So I'm still using bits for the size. However, I don't have to give it, like the final value is 9, and I know 9 has to be, or it needs like 4 bits to be fit in there, but like I can just take its log 2 or something. So what I can do is I can just go in here and say I need a local parameter. Okay, and that local parameter, I'm gonna call it bits, and that one here is actually just the C log 2 of the final value. Okay, the ceiling of log 2 of the final value. So if I decide, if I'm instantiating it with a final value of 16, it will take that and it'll know that I need 5 bits, and bits would be 5, and I've been using bits all along, so it just basically fits in my code. So now what else should I change? Frankly speaking, nothing. That's about it. This is how different it is between the input and the parameter. I believe what I did is I just moved it from the inputs and outputs. I made it a parameter. I just had it to use that local parameter in here just to see it. And I need a wire that is done, and here the final value is the parameter, and everything else is still the same. So let's see the result of the test bench here. And here's the result of that test bench. So in that test bench, I need to actually take a look at the parameter. I can't see the final value. Well, technically I can see it here because it's a parameter, but it's parameter now. It's not an input. It's never changing from the beginning of end. So what I did is I actually made that final value to be 19 in here. Okay, and then for the 19, I'm looking at it, so it's 19, that means it's modulus 20, so it goes all the way to 0, all the way to 19, and then goes back. If I want to actually change that particular parameter, all I have to do is just go in here and change it. So for example, you need something for let's say 500. Okay, you can definitely do that 500. I don't know if it will last for 500. I'll have to see. Well, I think it will. So let's do that here. And I'll show you why I thought it will be doing it. And yes, it did run it, so as I thought. So let me explain to you why I thought it will run it, and it ran it for a long time. So what I've done in here is I said I want to repeat final value plus 3, and the final value happened to be 500. So what it did, it's actually ran it like till it happened, like negative edge of the clock is 500 plus 3, which is 503 negative edge. So it will see it. You might not see it as per se, like it's actually counting towards the end, but you can actually take a look in here. So I will just try to zoom in here to just see. We'll zoom more so you can see it's actually 78, 79 all the way. And you can see that the final value in here is somewhere here. You can see it actually counted 500, and because it's modulus 501, since the final value is inclusive 500, then it goes to 0, 1, 2, 3, and 4, and that's because I added a few. I added like up to 3 like negative, and then I waited for 20 nanoseconds. If you run this code, it might not, you might not reach 500 directly. I have actually done something in here. I went to the setting, and I actually went to the simulation, okay, and then within the simulation I went here and I said the runtime is actually 1000 millisecond. I believe by default it's nanosecond, so it will stop at exactly 1000 nanosecond, which is not enough to run all of these. These are actually 5 million nanoseconds or so. So 1000 milliseconds is a pretty long time. Sometimes some simulations would require this, but it will take a long time to actually run these simulations. In this particular case, it wasn't too bad. It ran actually just fine. And just quick comment before I close this video, just make sure that the size of the counter is enough for the final value. If you decided to use the one with the input, for example, we did here the modular counter with input in here. If you decide to do the input here, the final value, you want it to be 500. If the number of bits you're actually choosing is 4, it's not going to fit and you're going to get some problems. This is a common error I actually make myself. That's why I'm mentioning it. Just like if you have to choose the size of the modular counter, just make sure it is actually enough to fit the final value.